Assalamualaikum and good day to all. This for the chapter 4.2 to 4.3, I would like to give you a video lecture on the topic of general material balance and also on how to label a flowchart. Okay. So this is the general mass balance. Okay. As we see, okay, for in this example is a reactor. There is two inlet streams. One is the hydrochloric acid. The other one is the sodium hydroxide. Okay, and eventually these two will react in the reactor and it will produce sodium hydroxide and water, which will be taken out at the bottom. Okay, there. So one outlet. Okay, so to explain this material balance, okay, we have to use an equation which we call general mass balance equation, whereby all the input through the system is subtracted by all the output of the system and plus all the generation. So in this case, you will have NaCl and water is the generation of the system within the system minus all the consumption. So the consumed NaOH and HCl is being subtracted, and all of this is equal to the accumulation within the system. Okay, in this case, which is the 1000 kilogram of water. Therefore, to make it easier for you to write, okay, and remember, we shortcut this into input minus output plus generation minus consumption, and this is equal to accumulation. To use this equation for examples or calculation, we can also simplify the general material balance according to some information given in the question. Okay, the first rule that we have, okay, is the balance is we doing for total mass or total mole, because we can either use mass balance or we can either use mole balance depending on the process and also the information given. So in this simplification for total mass and total mole, these two applies what we call conservation of mass, which means whatever mass that is coming in will always be the total mass that's come out, because mass cannot be generated, no, destroyed. Okay, therefore for this simplification, we can assume that the generation is 0. Okay, generation of mass as a total is 0, and the consumption of mass is 0. Therefore, we can eliminate these two from the general mass balance equation. Therefore, the final equation you will get accumulation equals to input minus output. This is the total accumulation equals the total mass or mole input minus the total mass or moles output. Okay. The next simplification, okay, if we have a substance that are non-reactive, okay, we can make further simplification as below. Okay, because for non-reactive species, there is no reaction. Okay, previously in the total mass and moles, okay, regardless whether the process are reactive or non-reactive, the total mass in will always equals to total mass out if it's a steady state. So the general mass balance will always be accumulation equals to input minus output, regardless of reactive or non-reactive. But for another simplification, and if there is non-reactive species, okay, So using the general mass balance equation, the generation and consumption will become 0 because there's no compound that is being generated, no new compound, thus, and as well as there's no compound that is being consumed. Therefore, these two terms are being set to 0. Therefore, okay, if we do the balance of the compound of each compound, for example, compound A, so the accumulation of compound A will equals to how much it is put into the system, which is the input of A, and how much it's being taken out of the system, which is output of A. So for this example, we have humidification of air, whereby we put in water and air. So we can make two balance equation using the compounds, which is one is air, the other one is water. So the accumulation of air will equals to the input of air minus the output of air. Same goes with water. The accumulation of water equals to the input of water minus the output of water. Okay, so this is different from the first simplification, which that one applies to total mass. Okay, so this only applies to non-reactive species. Alright, the final simplification, okay, that we can use in material balance is what we call a steady state system. Okay, if you remember the lecture in the second week, we have a steady state system and also unsteady state system. Okay, in this case, when we have unsteady state system, the amount of material in the system does not change. Okay, so if the amount is 100 kilogram, it will not change to 110 kilogram. Therefore, the accumulation is 0. Okay, then we can reduce the general mass balance equation from accumulation equals to input minus output plus generation minus consumption to all of this to equals to 0. Okay, so that is steady state. If further on you have a steady state system and the system is a non-reactive system, okay, so they have these two, okay, therefore the system has accumulation term must become 0. The generation and also consumption terms will also become 0. Therefore, the final equation is just input equals to output. Okay. So when you want to do material balance, there are several ways that you can do it. Okay. And almost all the time you need to do all the balances. Okay. First, most of the time you will start with total mass or mole balance, okay, where total mass in and also total mass out, it depends on the process. Okay, if it's steady state, then accumulations become 0. If it's not, then total mass in will minus total mass out equals to accumulation. So this can be referred to the first rule of simplification. So the next balance that you can do is what we call compound balance. Okay, so where we can do the balance for all the chemical compound that is in the process. Okay, regardless whether it's only in the reactant or whether it's only in the product, or it can be in the reactant and in the product. Okay, so it can be at inlet and also outlet, or either one of them. The next process is the next material balance you can do is we can use atomic species. Okay, and this atomic species balance is only applied for a reactive species. So later on you will learn on how to do the balance using atomic species. Okay, the final one is using volume balance. And this volume balance can only be used at specific cases, and as a rule of thumb, it's better not to use this. So whenever you get a volume as the basis, so you have to either convert it to mass or to mole accordingly. So, okay, the next part, okay. So in material balance, in a process, sometimes we only have one component, okay, in the process. For example, in this case, we have water inlet into a tank, probably, and it's coming out. So this is probably just a reservoir tank for a process in a plant, okay. So we call this material balance for single component. Okay, so the single component, of course, there will not be a reaction. Okay, there will not be a reaction in this process. Therefore, the material balance will become accumulation of material within the system equals to total flow into the system. Okay, flow because it's a continuous process minus the total flow out of the system. Therefore, okay, if we have a steady state condition, accumulation term will become 0, then the total flow into the system will equals to total flow out of the system. Okay, this is just a simplification. Right, then if instead we have a unsteady state condition for a single component, okay, so you will not have accumulation of the material equals to 0 because it's unsteady state. It's only happen for steady state. But the way to calculate is that the final material in the system, okay, for example, we have the mass, okay, the final mass is 300 kilogram minus by the initial mass in the system. Okay, so this is how we calculate. So, okay, if we have a non-reactive system for a single component, we can do a calculation on the non-reactive process by using general material balance equation, whereby we can use the amount of material in the system at time 2, okay, minus the initial material in the system at time 1, okay. This will equals to how many that is flow into the system minus the one that is flowing out of the system. Okay, so for the example of this, you can refer to the methanol mixture in the lecture notes. Okay, so in a lot of process, we will use more than one components. Okay, therefore we call this multiple component material balance. Okay, if we have a steady state condition, okay, for this process, whereby the total flow in will equals to total flow out. This is from equation 2 before. Therefore, we can make several material balance, whereby we call these component balances. Okay. In this example, okay, the inlet, okay, is for reactive or non-reactive. We have mass or moles of chemical compound. In this example, I give oxygen and also carbon dioxide, and the flow out will be the same compound, oxygen and carbon dioxide, or it can be an atomic species, okay, in and out. So for us to do a component balance, okay, we can use the same equation as before, okay, but the balance is for the specific compound. For example, a compound A, so we can calculate final component of A in system at T2 minus the initial component of A at the system at T1 minus the equals to the flow of A minus the flow of A out of the system. Similar can goes to B. So if this is steady state condition, flow A will equals to flow out. Okay, next. Okay, this is generally what you will be doing for your design, and this is a common layout for a process flow diagram. Okay, we have a lot of equipment, therefore we have a lot of streams, inlet streams and outlet streams, and also interconnecting between the units or between the equipment. Therefore, okay, you need to be able to show that each stream their information for a material balance. So PFD or PFS, whichever, is the same name. Normally we use PFD, process flow diagram, must comprise of all the elements below. Okay, so first you have to have all of the major equipment. Okay, so in a flow chart, we have to have all of this equipment, all of this in the list. First, we have to have all the major equipment. Normally, we will draw a box is the beginning, okay, for each of them. And all lines entering or leaving the process, and as well as lines that interconnect between the processes. These are called streams, okay, all input and output streams. Next, we need to have flow rate of each stream, so denoted in red color. Whether the flow rate is known or not known, they have to be written on the process flow diagram. The next one is composition of each stream. This also has to be put in, even if the composition is not known. Okay. Last, for this semester, you'll be also putting the operating conditions of each stream and or unit that you are using in the process. Okay, so you have to put at least the temperature and pressure of each process. Sometimes it's crucial as well to put the phase of the process. Okay, lastly, this will be done next semester, whereby you'll be calculating the heat or the energy needed or removed in the from the process. Therefore, you need to put the Q in or Q out of the process. Okay, but we will learn in detail next semester. So next, I will explain to you on how to do the labeling of the streams for the flowchart. Okay, there are two conditions. Okay, one, okay, if we have known variables, okay, for the streams, we have to put in the values of the known variables. In this example, we have 1000 mole per hour of air as in the input stream, and we know by heart that the mole fraction of air is 21% mole of O2 and 79% mole N2. Therefore, it can be written this way, whereby the top of the arrow will be the flow rate, the bottom of the arrow will be the molar composition. Another way to write this, instead of putting the total flow rate at the top, you can also put the component flow rate on the bottom. Okay, so this one is flow rate, so the unit should be per hour. So for O2, we calculate right away that the amount of O2 coming in is 1000 mole times 0.21, so you will get 210 mole of O2 and 990 mole of nitrogen. Both of these you should put on the bottom of the arrow. Okay. Next, if we have a question whereby we do not know the streams information, okay, we have to assign an algebraic symbols, okay, for the unknown streams. Later on, we will see which symbols should be used for what. Okay. And also we have to put the associated unit. Okay, so the first example is unknown flow rate. Okay, if given for you an unknown flow rate of mole flow rate, therefore we have to put the letter N naught. okay, not denotes for flow rate. And in parentheses, we put mole per hour, which is the unit. So on the bottom, again, similar to the top one, we will, in this case, we know the value because this is air, and the molar composition stays the same. So in this case, we will have 0.21 mole O2 per mole of air and 0.79 mole of N2 per mole of air. So the temperature and pressure for the streams should be written below this composition. In this case, it's 320 degrees Celsius at a pressure of 1.4 atmosphere. If the flow rate is known, but the composition is not known in the mass or mole, okay, so we have to also assign algebraic symbol. So for mass fraction, we put X. For mole fraction, we use Y. Okay, so for this example, the flow rate of air is flow rate of air. This is one example. The flow rate is 400 mole per hour. Okay, we do not need to put the parentheses because it's known. And the amount or the composition of the O2 and N2 is written as an algebraic. So this is mole, so we use Y. So we choose first the O2, so it's Y in parentheses mole O2 per mole. And for N2, we put 1 minus Y because we know the total composition of the stream must equal to 1. It can never be less than, more than 1, and it should be no less than 1. Okay, so instead of putting Y and X or Z, okay, another symbol, it's better to put the same algebraic symbol when it has a relation, something like this. All right. So this is because when we have we have unknown. Okay, when we want to do the labeling, we should keep it to minimum. Okay, because we want to have as little unknown as possible, so that is possible for us to solve the equation. Okay, this you will also learn in the next lecture under the degree of freedom analysis. So these are two examples. Okay, first, instead of, if you have a mass fraction, instead of putting x1 and x2, okay, but knowing that x1 plus x2 equals to 1, you can put x kilogram A per kilogram, and the other one is 1 minus x, similar to the example that we had before. Okay, the next one, another example, and is commonly being done, okay, is in the question says, if mass stream 1 is half of that stream 2, so instead of using mass flow rate 1 and mass flow rate 2, you can use this relation whereby m, stream 1 is m and stream 2 is 2m. Okay, similar like we have done before, an example of equimolar. Okay, so you know one is 0.5, the other one is 1 minus 0.5, something like that. So there is a relation. All right, so the next tips is that, okay, for the calculation, you need to convert all streams into one basis. Okay, if you need the answer in mole, okay, then it's better to convert all of the streams in mole basis. Okay, and vice versa with mass. Okay, another tips is that if you are given mole fraction, okay, so it's better to convert all the flow rate or the amount into mole instead of mass. Okay, because you cannot easily convert mole fraction to mass fraction directly. You need to use molecular weight and so on. So it's a bit hassle. So it's better to use mole basis if given the composition in mole, similar to if given a mass fraction. So you better use all of the streams to be in mass fraction. Another tips on this, which you will use in reactive process. Okay, in reaction, we will use mole for the calculation. Therefore, it's better to change all the bases into mole. All right. If given for you is the volumetric flow rate, okay, so you need to first convert either to mass or mole flow rate, because we do not normally do the mass balance in volumetric flow rate. Okay, for the labelings, okay, for mass or amount, we use M, mass flow rate, M dot, and moles, N dot is mole flow rate. Volume is V, V dot is a volume flow rate, and X is normally component fraction in liquid, and Y moles fraction in gas. All right. The next one, which is a final one, is the basis of calculation. This basis of calculation is something that you should have, okay, to perform the material balance. Okay, normally it is an amount of flow of one stream or components in a process. Okay, first step is for a calculation of material balance is for you to choose a basis. Okay, so because we also need to calculate the unknown quantities, so we will use this basis to calculate all those unknowns. Okay, so what's the tips to choose a basis? Okay, if we have a stream given the amount of flow, okay, normally this is the best basis to use. Okay, because all the other unknown variables that you calculate, the unknown values that you calculate will be following this basis. In this example, we have 300 kg per hour of air to be humidified with water, which will be used in the gasification process to produce gas with composition of 10% hydrogen, 20% carbon monoxide, 5% methane, and the rest is carbon dioxide. So you need to find the amount of water needed for the process. Okay, therefore, okay, to find the amount of water, which is the unknown, you should therefore use the amount of air given, the flow rate of air given, which is 350 kg per hour of air, which is your basis. Okay, so another example is this one. In the first example, the feed is given as the basis. Okay, so for the second example, we have the product is given as the basis. Here we have methanol is produced using synthesis gas. 1 ton per day of methanol is needed to supply for a market in the area. How much synthesis gas should be supplied to the process? Okay, so in this question, the product of methanol is given, and this could become the basis for your calculation. Okay, the reason I say could is because it's possible that you should be using the next tip that I will give you instead of using the production. Okay, but it really depends. Okay, later on the question. So probably it's most convenient to use this basis. Probably you should also to use another basis for this type of question. All right, so if no stream amount of flows are given, okay, you need to assume a value. Okay, so how do you choose which stream to assume a basis? Normally we will choose the stream that the composition is known. Okay, or else it's going to be tough to do the mass balance calculation. Okay, so number one, if the mass fractions are known, okay, normally we will set the total mass or total flow of that particular stream as the basis. So take a look at the example whereby in this case we produce saline by mixing tap water and sodium chloride. A saline of 10% by weight, which is the product, is required for optimum living environment for marine species in the aquarium. So you need to calculate the amount of NaCl to be used to produce the saline of 10%. Okay, so because the saline is given, okay, it's good to use this stream. Saline mass fraction is given. It's good to use this stream for a basis. For example, we can put 100 kilogram of saline to be produced, right? So the next example, we have if the mole fractions are known, okay, then you choose a total number of moles or molar flow rate instead. Okay, so the previous example is on the mass fraction is known. Here we know the mole fraction. In this example, we have a reaction of methane and oxygen to produce formaldehyde. Okay, so the feed contains equivalent amount of methane and oxygen. Okay, with a fractional conversion of 0.9 and fractional yield of formaldehyde of 0.55, you need to calculate the molar composition of the reactor output stream. Okay, so in this case, you know that the amount of composition that need to be calculated is a molar basis. So what you can do is you can choose a basis of 100 moles of methane and oxygen. Okay, because also you know the amount of methane and oxygen in the feed. Okay, right? So choose the basis you can choose in this question, either 100 moles or 100 moles per second or 1000. It depends on the usage. All right, so that's all for this video lecture. Hope it helps you to understand more on the topic. So till the next video. Assalamualaikum.